Hello everyone. We discuss contest 9 today. So first problem is simple. So we just need to do what's written in the problem statement. So in the problem statement you have some story, like you have two people in the beginning and you have a number of operations. In every operation you swap one of the people. So you take one of two names you have currently and replace it with some another name. And you just need to tell what is the current state at every moment. So in the beginning you have these two names. After every operation you have some another two names. You need to just output which two names you have after every operation. So pretty straightforward, no tricks here. Just need to do what's written in the problem statement. So let's do it like this. Let's make a vector of two strings. And read first and second. Now read n. Let's output them. Now every time I read two strings, let's take A and B for simplicity, and I will just replace one of them. So I'll say if S0 equals A, I'll just do it like this, S0 equals B, else let's say S1 equals B. Just like this. So it's not the best code in the world, but it works. Okay, that's the most important property of the code. So it should work. If it's not very beautiful, it's okay. So for the first problem especially, the important thing, you don't overcomplicate. So code is not complicated. It's just not very pretty. Yes, but it does the job. Nothing interesting here. So first problem is not very interesting, but usually the first problem is just to give you some start. So you just remember that you participate in a contest, remember how to write programs and so on. Nothing really interesting, but still it's a programming problem. Okay, it will pass eventually, I believe it. So let's go to the second problem. So let's talk about second problem. So what have in the second problem? We have it's a nice problem with long problem statement, some pictures in the middle. So it's okay. No, it looks like actually programming problem. So what we have here? We have some sequence of beds. Why not? And some of them contain tabs. Yeah. So some of them have this like this red square. They contain some tabs. What does it mean? This tab just produces water. So what we have, if it's turned on, I believe all of them turned on. Yes. So it will create the water, and water will spill in both directions. So after some number of steps, you will fill all the beds in some segment. So you go to j-1 cells to the left and j+1 cells to the right. And just like especially in that, so they just write it in bold, so you cannot misread it. So you can't fill half of the bed. So it's discrete. So you just make only integer steps. You cannot make 2.5 steps here. And we want to turn on all the water tap at the same moment, and so what is the minimal number of seconds until whole garden is watered? Okay, so the problem is like this. We have this. Let's draw it actually. So we have some array of beds basically, and some of them contain tabs. Let's say here, and so on. And they start to spill water. So in the first moment they spill water only here. In the next moment they fill all the neighboring cells. in the next moment they fill these cells, and so on. And we need to find the minimal number of steps we need to take until every bed is filled with water. Multiple ways to solve this problem, actually. In Hux you have, not sure why. So, do we have picture? Oh no, we don't have picture, but we have this node. So sometimes it's fine. It's useful to read this node. So you can look at the first problem. It's only one example. So you can look at the example, and then we'll explain you what's going on in this example. Let's try actually. So in the first step we have 5 beds, and only one of them has tab. So we have 1, 2, 3, 4, 5, and we have tab in 3. Yes, so it's here. And they say we need 3 steps. No, yes, we need 3 steps. So we have first step, then we have second step, then we have first step. Yeah. So after 3 steps, we filled everything. So in the second example, we have 3 beds, and we have tabs in all of them. Yeah. So after the first step, we'll fill all the beds. So multiple ways to solve this problem. No, you can just simulate the whole process. So you can just, since we have only 200 elements, you can just simulate it. So you can make operations one by one. Every time you make the tab, fill everything. Now every time you fill units, so you every time for every tab you fill 2 more beds with water. So you can just simulate it. Every time you take all tabs, fill these 2 beds with water. Continue. Find this. Continue until you have all the beds filled with water, and it will work in something like 200 square probably. Yes, we also have even if you have 200 cube, it will work. So it's not problem not about time complexity. It's just for implementing any solution. I will implement fast solution just because it's maybe more for educational purposes, and actually it's easier for me to implement. So how the fast solution works? You can do the same in very good time complexity. So you have some tabs. So I'll remove this. So you have some tabs in some positions here. So first of all, you have this leftmost and rightmost tabs. This leftmost tab must fill everything to the left. So all these beds must be filled by this tab. Now, every bed is filled by the closest tab. Yes. So this tab must fill all these beds to the left. So we'll just count number of beds here, and it will be just, so this is the minimal number of steps I need to make to fill all these steps. Same to the right here. So all these beds must be filled by this step. Yeah. So I know number of them. I know number of the steps I need to make. Now for everything in the middle of between two steps. Yeah. So I need to fill it with. I fill it from 2 directions. I build it from left using this step, and I build it from the right using this step. Yeah. So number of steps is actually half of the size of this step. So half of these beds will be filled by one, and half of them will be filled by another. And now we just need to carefully divide it by 2. Yes, because if it is even, it's divided evenly. If it's odd, so one bed will be in the middle. So let's try it. So let's see. So imagine you have distance between these 2 tabs. So imagine you have 2 tabs and distance between them is d. So I have them, then I have something. Let's make it odd to make it interesting. Yeah. So how I usually do it? I just draw a small example like here distance equals 1, 2, 3, 4, 5, 6. So if distance equals 6, then I have some odd number of elements in the middle. So what should be the answer? The answer should be, so I pick, so it's 1, then I have 2, then I have 3, then I have 4. Yeah. So after 4 operations, I will fill everything. So it's again 1, 2, 3. So 3 is not enough, but 4 is enough. Yeah. So it should be 4. So answer is 4. And if I have say even number of elements, let's see. So for d equals 3, yeah, the answer will be 2. Yeah, so I have 1 and then 2. So I have 1 and then 2. Yeah? And now we just need to guess the formula. So again, there are many ways to find this formula. You can use some mathematical thinking, or you can just guess. Sometimes it's just easier to guess the formula. So I know the formula should be something like distance divided by 2 plus minus 1 depends. Yes. So if I divide 6 by 2, I will get 3. If I divide 3 by 2 and remove the remainder, I have 1. Yeah. So it looks like these numbers. Both looks like d divided by 2, yes, floor of this, yes, plus 1. So again, you can find this formula just by applying some math on some math reasoning, or you just can try it on small examples and just guess the formula and see it works. Whatever is faster for you. In the contest, you basically optimize your time. So you try to get this formula as fast as you can. Yeah, and preferably not to make any bugs during this. So if the formula is not correct, it's not good. So I found this method by just minimizing amount of mistakes I make. So if formula works for some small we left another box. Okay, only one student left. Okay, so that's it for you. So I found this method by just minimizing the amount of mistakes I make. So if formula works for some small integers, it probably also works for big integers. So if I know formula should look like this, and it works for small integers, it probably works always. Okay, let's solve the problem actually. So I'll use my multi-test template. So what we do? So we have n and k, and we have number of steps. Okay, so I added all the data and I just sorted. And yeah, now again, let's start by, okay, so let's make special variable for result and just let's calculate the result. So first of all, I need to fill these elements to the left from the first step and to the right from the last step. So let's start from this. So it will be maximum of these two elements. It will be maximum of many elements. Yeah. So first element is distance from the leftmost step is a0. To the left is just a0. Yeah. So I need number of elements including a0. So they number from 1. So it's very conveniently. So for the last one, so for this one, I need number of elements from the last step to the end, including the last step. So again, you guess the formula. So it should be something like n minus k minus 1 plus minus 1. Yeah, and you guess this plus minus 1 just by trying. So you try to put the last one. So if the last step is in the end, so if this value equals to n, the answer should be 1. Yeah. So if I have step in the last bed, then I need one step to fill this last bed. Yeah. But if I put it in this formula, I get 0. Yeah. So it looks like it should be plus 1. Yeah. Now for every segment between two steps, I just use this formula. I calculate distance. And and just update my result. So get this divided by 2 plus 1. Well, that's it. Pom, pom, pom. Problem basically about some clever implementation. You see, so this is the whole solution. So this is the whole solution. It's pretty short, and nothing really complicated is going on here. You may write your own solution, and it may be much more complicated than this one, but it's fine. If you make it work, it's good for you. Problem C. In problem C, we have it looks like chess problem. Chess problems are probably scary. So if you read the problem is about chess, you think, oh no, I need to implement all this chess stuff and so on. In this problem, actually not. So it's only name is about chess. Its problem itself is not about chess. So what we have? We have a board. So the only thing is from chess is the coloring of this board. So we have a one-dimensional board. So it's 1 by n, and it's colored with like alternating black and white cells. Now we have some chess pieces. So these again, it says chess pieces, but they don't tell which pieces, so because it doesn't matter. So it's not about chess. So we have some pieces. Basically, we have some tokens put in some cells, and we need to move them to some positions. Positions. Yeah. So we need to move them in positions with the same colors. So there is exactly n over 2 pieces, and we need to move them in all white cells or in all black cells. There are 2 options. And we do it by moving pieces one by one in one operation. So in one move, we move one of the pieces, just one position left or right. And we need to minimize number of these moves. So again, n is small, so you don't care about time complexity, but I will present you a very fast solution actually, just because I can. But it's not about time complexity. So you may find another solution with worse time complexity. It will still work. What is the idea? It's actually a pretty common idea in problems like this. So let me just talk about similar problems. So you may be seen similar problems before. Like you have some linear structure. You may have, in this case, you have a linear board, or you may just have like integer line, and you have some tokens standing in some different positions of this line, and they start in one positions, and you need to move them to some another positions. Yeah, like this. And the idea is that if you allow to move every person and you minimize total, basically when you minimize total distance, yes. So minimize total number of moves is the same as minimizing total distance we move these tokens. And when you minimize total distance in one-dimensional case, you just basically you never need to change the order of elements. So because if you have 2 elements, you may say element x and element y, yeah, and they start in these positions, but in the end they are in these positions. It means you move x here and you move y here. So at some point they need to meet in the same point, but it means so you move them here and then swap them. Yeah. So y goes to the left, x goes to the right. We can, instead of this, we can swap them again. So we can swap them here. So x go here and y go here. So they finish in these positions. So x goes here, y goes here. Total distance is the same, yeah, but they preserve the same order. So what does it mean? It is never optimal to change the order of elements. So if they go in this order, 1, 2, 3, 4 here, they must go in the same order here, 1, 2, 3, and 4. And now to calculate total distance, we just need to calculate distance between elements with the same number. So this 1 goes here, this 2 goes here, 3 goes here, and 4 goes here. Now, depending on the problem, we do something else. In this case, we just need to, we know the positions, yeah? So in this case, no, kind of, no, we have two options. We have all black cells or all white cells. And from these two options, we just pick the minimal one, yeah? So in some another problem, you may have the same structure, but you need to calculate something more interesting, probably. But not in this problem. In this problem, it's very easy. So we just need to calculate the total distance. So let's do it. So we have n, and we have this vector p. Oh. And we're talking. My fingers don't work today. Okay, so from 1 to n. Okay, nice. Now let's sort them. Now we have two options again. We have options to put them in all white cells and in all black cells. So we either put them in positions 1, 3, 5, and so on, or we put them in positions 2, 4, 6, and so on. Yeah? So I usually write comments like this just to clarify. Okay, so it's not comment for people who read this. It's problem for me. So it's fine. So I need to consider these two options. So I will pick this first element and start from it. So the first element will be either 1 or 2. Yeah. So here is the first element. Now I need to. So the element with index I will be s plus 2 multiplied by. Yeah. Or you can do it like this. You make x, you might find x, put it to s, then every time you make x plus 2, like this. Up to you. So both methods work the same. So now I have position x. So I'll just calculate the result. So calculate sum equals 0, sum. So I need to find the distance between x and pi. And now I just calculate minimum of these two cases. Let's go like this. Oh, that's it. So again, problem is not very hard, but it shows some important techniques actually. So again, I believe the most important lesson you can learn from this problem is actually this one. So so when you move points in one-dimensional problem and you minimize total distance, then you just need to move them in such a way that they finish in the same order as they started. And that's it. Everything else is actually just technicalities. So after you find this, so if you didn't know this trick before, after you learn this trick, everything else is just pure implementation techniques. So it's nothing interesting here. So here is just simple implementation. Problem D. We have a long, complicated statement. It looks something about graphs. So when you start reading it, you think that it's problem about graphs. Okay. So I have some cities and roads, and so here we have some rules how this graph is constructed. So we have n cities. Basically, you have n vertices of your graph, and k of them are capital cities. So we have some k special nodes in graph, and you have some beauties. Okay. So you have some numbers assigned to all the nodes. I'll just translate this problem statement to some mathematical, okay, to pure formal. So we have n nodes, k of them are special, and each of the node is assigned some value ci. Now, how the graph is constructed? So we construct the graph by making this cycle. So we connect roads between cities 1 and 2, 2 and 3, and so on, and in the end we connect n and 1. So we make this big cycle of all the vertices. And here, additionally, we connect every capital city to all other cities. It means we take all these special nodes and just connect them to everything else. Yeah? So they already connected to neighbors, so we just connect them to all other nodes. So this rule just said that we don't produce multiple roads of the same type. So when we create a capital city, we connect, so it's already connected to neighboring cities. We just connect it to every city is not yet connected. Now we have some prices of the road. So price is just number assigned to the road. Yeah? So it's nothing really special, but so we have these numbers assigned to all the vertices, and we just assign these numbers to all the edges. Yeah? So number assigned to the edge equals to product of these two numbers. Now, what we need to calculate? In the end, we need to calculate the total. Okay, so what was it here? So we need to calculate total sum of all numbers assigned to all the edges. So every edge is assigned this product. We just need to calculate sum of all these possible products. Yeah? So we need to calculate sum of all these products for all pairs of nodes connected by the edge. That's it. Here, formally, it's right, especially specifically what I just said. That's it. Now let's look at constraints. So since we're reading this problem statement, let's look at constraints. So n is pretty large here. So you need very efficient solution. So you cannot just construct the graph, because if you just construct a graph, for example, if all nodes are special, if all cities are capitals, then you may have up to n square edges. Yeah. So you have n square edges. You can't calculate sum of all these n square products fast, because if n is up to 10 power 5, 10 power 10 is a little bit too much to do it in the time limit. So we need some efficient way to calculate this value. Now you can read, you can get to here, think about, will I have any problems with integer overflows? Okay, so I have numbers up to 10 power 4. If I multiply them, I get number up to 10 power 8. Yeah, so one product will fit into 32-bit integer, but some will probably not, because some will be, okay, I need 10 power 10 multiplied by 10 power 8, but the sum of all these products will fit into 64-bit integers. It's also okay. That's it. Now you can look at the so they also give you some nice pictures for the examples, so you can just look at them and think about them. That's okay. So this is how my graph looks like. I have a cycle plus some edges in the middle. Yeah. So we have this cycle here and also some edges in the middle. No, okay. How do you solve problems like this? No, again, you need to calculate some sum. Yeah. So let me write some. So it looks like a graph problem. It's actually more like calculation of sums. Yeah, so it's not about graphs. We just construct a graph. Then we don't use any properties of a graph. We just calculate some sum of products. So you need to calculate sum of products Ci multiplied by Cj for all pairs ij connected by the edge. Let's first solve some easy cases. So before you move to the full problem, it's usually good to think about some easy cases. For example, if I don't have any capitals, so if I only have this big cycle and nothing else, then it's easy to calculate this sum. You can calculate it just by going around this cycle. Yeah, so you have linear number of edges. So you can just take every edge, calculate this sum. Yeah. So it will be just sum of like Ci multiplied by Ci plus 1. Yeah. So it's easy. So if you don't have any capitals, it's easy problem. Now, when you have capitals, let's move to other end of this line, yes? So if you have only capitals, so if every city is a capital, then you have all possible edges. You have a lot of edges. You have many edges. And this, yeah. So you have a lot of edges. How to calculate in this case? So now I need to calculate sum for all pairs of, so you need to calculate sum for all I, sum for all j, ci multiplied by cj. Okay, so it's sum for all, but only for I less than j, yeah. So I need to sum for all elements, but so multiple ways to do it. So easiest way is to do it like this. Let's get rid of this inequation. I don't like it. No, because of reasons. You can do it like this. So if I remove this inequation, so I calculate for all pairs, just for all I from 1 to n, for all j from 1 to n. So imagine I can calculate this sum. So how can I get from this sum, how this sum is different from the sum I need to calculate? It's actually almost the same. So I have every pair in this sum, but some pairs I have twice, yeah? So some pairs you have multiple times. So you have pair uv, and also you have pair vu. So you have pair uv and you have pair vu. So you calculate it twice. So you can just divide it by 2, and it's almost correct. Yeah? But also you have problem when you have I equal to j in this sum. So because I don't check that I is not equal to j. So I can just subtract it. So you subtract sum of ci multiplied by ci. Yeah? So you get sum of all possible pairs. Subtract pairs of 2 equal elements. Now you have only sum of 2 not equal elements. And then every pair of not equal elements you have twice in this sum. So I can divide it by 2 and get something. Now for this sum is actually easy to calculate. So it's sum of all possible numbers, of all possible pairs. No, you can easily calculate by this. This sum is just sum of all ci multiplied by sum of all cj. You can just move this ci out of this sum. See? Now this sum does not depend on I, so you can just swap it like this. So it's basically a sum of all elements square. It actually makes sense. If you take sum and calculate square of the sum of elements, you will calculate a sum of all possible products of all pairs of the elements. Okay, that's one way to solve this problem. Another way to solve the same problem is like this. So I'll just show you all possible tricks that you can use here. The more tricks you know, it's easier it is to solve problems like this, because you never know. So usually there are multiple ways to solve the problem. Yeah, but if you know many tricks, you will more probably recognize one of them and use them. Yeah. So another way how to solve problem like this. Again, yeah, I want to calculate sum of all. Let's say so I j such that I is less than j. Let's say ci multiplied by cj. Let's do it like this. So here are my elements. Yeah. So let's go one by one. Pick one of the elements. Now for every element, I need to multiply. Let's pick element j. Yeah. So for this element j, I need to multiply it to all elements before. Yeah. To all these elements and calculate sum. So let's write it like this. So I take j from 1 to n. Then I take all elements I from 1 to j minus 1. Okay, let's do it from 0. So it's easier to translate it to the code. So in my code it will be zeros. So you take j from n minus 1, pick element j. Yeah. Now you need to consider all elements to the left and calculate this product ci multiplied by cj. Now again, from this sum, you can put this j out of the sum. J is the same. Yeah? So it will be the same as we take elements j from 0 to n minus 1. Here we multiply Cj by the sum of all elements Ci on the prefix from 0 to j minus 1. It makes sense. Again, we multiply this Cj by all the previous elements and calculate sum of these products. It is the same as we just calculate sum of all elements and multiply this sum by elements Cj. Yeah? So we take elements Cj and multiply it by the sum of all previous elements. Now we can just calculate all these sums. Yeah? So we go from left to right and just every time we know this sum of all previous elements moved at s. Yeah? So every time we take element Cj, multiply it by this sum s, add this product to result, and then move to the next element. When we move to the next element, we just increase this s by this number Cj. So we just expand this segment by 1. It's another way to do the same. Now, let's try to use some of these tricks to actually solve the problem. Let's go. So how would I solve problems? So, first of all, let's take some capital cities. So you have some capital cities. Let's make 3 capital cities and some small cities here. So every capital city is connected to all other cities. So let's calculate for every capital city sum of all the edges connected to this city. Now it's easy. So if I have capital city Ci, I need to multiply Ci by sum of all elements Cj, j not equals to I. Yeah. Again, I need to calculate sum of products. I need to multiply Ci by all elements Cj and then calculate sum of all these products. It is the same, it's just multiplying Ci by sum of all other values. That's it. So now I can for every capital city calculate sum of all roads connected to this city. That's fine. Let's do it for every capital city. So I do it for this city, I do it for this city, I calculate all this, I calculate for all this, and so on. Now, I calculated everything here. Now, some roads are calculated twice. So if road is connecting 2 capital cities, here, here, here. So these roads are calculated twice. So I need to subtract this value. So this sum calculates sum of all roads. Now I need to calculate sum of all roads connected only capitals and subtract from the sum. And also in the end I need to go around this loop and around this how it's called, cycle, and count all the weights on this cycle as well. So that's one way to do it. So again, for every capital city, I will calculate sum of everything except this capital city. This way I will count all the roads connected to every capital city. Now, if road is connecting 2 capital cities, I will count it twice. So I can subtract it in the end. Also, I didn't calculate roads on this cycle. Initially I have this cycle, yeah. So in the end I will go around this cycle and calculate these sums as well. Just linear number of edges, so I'll calculate them. Okay. Okay, hope it's clear enough. Now, there's one way to do it. So actually, easier way is to do it like this. So I will. So I don't need to subtract this actually. So okay, it's actually a fine solution. We can implement it just like this. But I don't want to subtract these roads connecting 2 capitals. Yeah. So instead of subtracting these rows, I will just subtract this sum. So I will get the sum of all elements except I and except all previous capitals. Well, let me show you how. So I have N, K, deposit K, K. I have number C. Make them longs. And capital cities. Okay. ID is a bad name. Let's make them X. It's from 1 to n. Let's make it from 0 to n minus 1. Yeah. So all indices are always from 0 to n minus 1. Now, I will just apply this technique. So again, I will look through all capital cities. So I will take all. Okay, let's do it like this. So I'll take all capital cities one by one. Then I will calculate this product. I will multiply Ci by sum of all values except I and except all previous capitals. So I calculate sum of all cities. So it's S equals 0. Let's do it like this because I can. I reuse value X. Not the best way to program actually. Okay, let's call it somehow. What letters I didn't use? E. I will use only one letter in identifiers until I'm out of letters. Okay. So this is my sum of all elements. Okay. I need sum of all elements except my current element and except all previous capitals. Yeah. So I will just here I will remove my element from this sum, and now I need to calculate my Ci multiplied by this sum and add it to result. That's not it. We still need to add all the edges on this main cycle. But let's just so I calculated sum of all rows connected to all capitals. So the number we have now should be less or equal than the actual number. Yeah. So let's check this. So we calculated something. So we have 7. What is 7? Let's go here. So in the first case, in the first example, we have single capital 3. This 3. Yeah. So this 7 is sum of 2 and 3. It is 7. Yeah. Works okay. 61. Again, 61 is less or equal than 71. So we'll calculate sum for some edges, not all of them yet. Yeah. So it should be greater than 71. That's okay. So that's what we check. We also can check that the sum is actually correct. So we have two capitals 1 and 4. 1 and 4. For 1 I have sum 15 plus 6. Okay, that's too much. No. We have calculator. Okay. We have 15 plus 6 plus 6 plus 12. And for the 4 we have plus 4 plus 10. 6 already counted plus 8. 61. Looks okay. Okay. It's actually it's important to check that you didn't make any bugs in the middle of the process, because if you only check the final result, then even if it is correct, you may have some problems in the middle. If it is not correct, you may have many problems in the middle. Yes, so you don't know where you actually make the bug. But so it's good to check few times in the process that your current result is actually okay. So. Okay, now let's finalize it. So now we need to add everything on this main cycle. So let's go. So I have this edge between I and j. Yeah, so this is my edge on the loop. Some of them I already calculated. So if it's edge connected to some capital, then I already calculated it. So I will check. If it is not capital, I need to check which nodes are capitals and which are not. Vector boolean, let's say capital. Let's say x, let's say true. So some of them are capitals. So I didn't count the edge if both ends are not capitals. So because previously I counted everything connected to capitals. So if edge is not connected to a capital, I didn't count it. So I check if it is not capital I and it is not capital J. So if both ends are not capitals, I didn't count it before. So I'll just count it now. So I take equals Ci multiplied by Cj. That's it. So now it should be okay. So now I counted everything. 17 looks fine. 71 looks fine. So again, the problem is not about graphs. The problem is about calculating sums. And more problems like this you solved before, easier it is for you. Again, the problem is calculating sum of products. So say you calculate sum of products like this. You do it by, again, how you calculate sums. You split the sum into some parts, easier to calculate. So what I did here, I take sum capital and take the part of this sum that contains all elements connected to this capital. Group them, yes, and calculate them easily just by multiplying weight of this element by sum of all weights of other elements. Then take another group, calculate sum of this group, and so on. Yeah, so here I calculate sum of group of elements. Not a single element, but every time I calculate a group of elements. Yeah? And by doing this, in the end, I have the total sum. No, that's it. I don't know what else to tell. So, not the easiest problem, but it's not very hard. Again, if you solve multiple problems like this before, every time you solve this problem, every next time you solve the problem like this, it's easier and easier. So just get some practice solving a problem like this. Let's read some of your solutions. Who's first? Maris was first. Okay, here we read all the statement. Boom, boom. Okay, so here we marked all the capital cities. Okay, here we calculate sum of all elements on a cycle and calculate total sum. Okay, a little bit more complicated here. So what we're doing here, we calculate sum of all elements on the cycle before. So when we calculate sum of edges connected to a capital city, we just don't calculate if it is already calculated before. So we kind of remove from this sum two neighboring edges. Also possible. Again, you just group the elements in different way. Also works. So it's just small adjustments. Basically, there's small details. Overall, this solution is the same. So I calculate elements on a cycle using simple loop because it's linear number of edges, and here I calculate everything connected to every capital. Yeah, and that's it. Yeah, you just move this calculation from here to here. I have special calculation here. You have special calculation here. Yeah. Overall idea is the same. Good. So what we have in problem E? We have again some long strange process happening here, and you just need, basically it's data structure problem. You need to create the best data structure suitable for this job. So you have some strange situation. You need to calculate something. So you have some basically you have some queries. Yeah. So you have here are the queries. and you need to count it. So you make these queries, they change something in your data structure. Basically, you need to maintain the unread notifications. Yeah. So you have some notifications, you make some operations with the notifications, and what you need to do, you need to, sometimes you need to tell how many unread notifications you have now. Yeah. So you have these queries that changes something in your data structure, and you have query which asks you something. Yeah. So you have query, give me number of unread notifications. No, and you basically call it every time, yes. Okay, so after every operation, you need to answer what is the current number of unread notifications. Nice problem. So because again, in some of problems like this, you just use some of normal data structures like priority queue, set, something like this. Here, when you have something like this, you actually need to improvise. So you need to invent a new data structure or combine some existing data structures and so on. So I love problems like this. There are a lot of them, but all of them actually exist. So, and what I love in this problem is actually a problem statement is kind of natural. So it's something that may happen in real job. So in some real project, you may have situation like this. You have some notifications. There are some operations with them happening, and you need to answer what is number. Probably you will have not. So I believe you have not that many notifications, but who knows? Probably you don't have that many notifications, and probably you don't have that many applications. Yes, but who knows? So in some other project, you may have a lot of situations like so. So problems like this are actually quite natural and may happen in real life, and that's I love about them. So let's see. So what we have? We have some notifications produced by some applications. Yeah. So we have some application. Sometimes some of them generate some notifications. Now, what we do? Sometimes we read all the notifications generated by the same application. So we take some application X and mark all notifications as read. Yeah. Now, sometimes we also read some first T notifications. So we have, let me show. So we have some. Let's read the first example. Oh, can I put them in the same screen so I can read note and? I'm not sure. I have some allergies, so that's why I'm sorry. Like this. So let's read the first example. So in the first example, I have following situations. First, I generate, so for application 3 generate a notification. Yeah. So first notification generated by application 3. Now application 1 generates. So now application 1. Now application 2 generates. Now I have 2 notifications, or 3 notifications generated by 1, 2, 3. So I output 1, then output 2, then output 3. Yeah, like here. Yeah. Now I read all notifications by the application 3. So this notification is read. Now I have only 2 notifications. So this is the output. Easy. Let's read the second example. Again, it's fun. It's fine to read examples and just write down what's happening to you better understand what's going on in the problem. So I have notifications from applications 2, 4, and 2. So I have 1, 2, and 3. Then I read all 3 notifications. Yes. So you read 3 notifications. So you mark them as read. And now you add 2 more notifications by 3. So you have 3 and 3. So you output first. You read them also. You output 0. Then you output 1. Then output 2. Everything makes sense. So again, you read the examples to make sure you understand the problem statement like it's supposed to. Now, how we solve this problem? No, many ways to solve this problem. Let's do it like this. So, what I will do? So, What's the easiest way to solve the problem? No, let's consider only first. So let's consider only notifications of the second type, so only queries of the third type. So here. So imagine you do it like this. So sometimes you have some new notifications, yeah, and sometimes you read all the previous notifications. So sometimes you read all the previous T notifications and mark them as read, right? So imagine you don't have operations of the second type, only 1 and 3. Yeah. Then what we do? What we need to do? So you have some sequence of notifications, yeah, and you always read some prefix of it. Now, what you need to remember? So always have situation like this. Yeah, you have a lot of elements. Some prefix is read. So what you do when you have operation of this third type? You just check. So I need to read these notifications. So if this T is greater than your current prefix, you have some current prefix which is written. This is P. So P first notification already read. So we check if T is greater than P, then I need also to read all these notifications as well. So that's all with this operation of third type. So if I only have operations of type 1 and 3, yeah, all I need is to maintain this one integer, like length of the current prefix. This current prefix is already read, and when T is greater than P, I read all these messages and make P equal to T, and that's all. Now, when I have operations of the second type, what I need to do? I need to read some messages in the middle. So when I have something like this, so you need to find all the messages of the application X. So you have like application X here, 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 here. Yeah. So you need to find all these messages of application X and mark them as read. Yeah. So we need to maintain all the messages of the same application. No, let's do it. So let's maintain the positions of all messages of the same application. Yeah? Then we can iterate over all of them and just mark them as read. So I will look through all elements equal to X and mark them as read. If it is already marked as read, I'll just skip it. Okay. So again, for operation 2, I just need to maintain the basically list of all occurrences of the same X in my total sequence. No, that's it. Let's just implement it. So let's go. So it should be easy. What we have NQ. Let's do it like this, just to make it look fancy. Now, do we know how many X is up to N? Okay, let's make vector of vector. Pos. Let's say +1. So it's 1 to N. Just like this. So this will mark all the positions of the notification of the same application. Yeah. So for every application, I will mark all the positions of this application. Now I need this end P. It will just tell me a number of the first notifications I already read. Yes, and I need 0. And I need to have the current sum. Yeah, so this is my result. It's called result. And I need this Q, yes. So I need to, for every notification, I need to maintain current state. Yeah, state will be false if it's not read, true if it's read. No, I think that's it. Now let's go. So we need type. So if type is 1, I need to read X. Now I have new notification of application X. So I add pushback false. So I add another unread message to my sequence and added position for X. Position will be just size -1. It is the last time, yes. So in increase size bar, okay. So res is the number of unread messages. So here I add one more unread message from application X. Yeah, I added to my sequence of unread messages. I added to all the positions of application X and increase result by 1. Okay. What? Boring. Well, now if t equals 2. If t equals 2, then, okay, let's keep it for now. 2 is more complicated. So if t equals 3, I need to read first t notifications. So let's read t. Now we check. If this t is greater than p, then I need to read first t notifications. So I will have p equals t, but before I need to read first t notifications. Let's just read one by one. Just do it while p less than t, like this. I will just read them one by one. So I check the p++. Yeah? So if it is not read, I will read it and decrease the counter. So here I just simply read first t messages. So I always have some prefix of read messages. So if my current prefix is less than prefix I need, I just extend my current prefix until I have all these messages read. Okay. Finally, when I need to read all the messages by the same application, I will just look at all messages of the same application. I need to read X. And mark them as read. So if it is not read before, I will read it and decrease counter. Now, in the end, I will remove all these positions. So I don't iterate over them multiple times. If I already mark them as read, I can remove them. So I just clear all these positions. I think that's it. Looks okay. What? Oh, okay, you don't like me to use. Okay. Let's say type. Okay, let's keep it like this. That's it. That's the whole solution. Again, problem is about careful combining data structures to make the data structure you need. In my case, this data structure is just number of arrays. I have array here. I have arrays of arrays here. Vectors of vectors. So for every, again, I need to. How you solve problems like this? You think, okay, what I need to remember to make the separations fast. And you see, okay, I need to remember the positions for each application. So when I need to remove, to read all the notifications by the same application, I just need to remember where are these notifications. So I need to maintain the positions for every application. And okay, you can do it. You can, for every application, make this list of all positions. That's it. That's it. Let's actually check what you have in these problems. You have sets. Okay, why not? You don't need sets, but you can use sets. Why not? So what do we have? I have set this, and I have array of sets here. So again, I believe what you're doing here, you just iterate all of them. Yeah. No, yes, you just take all elements from the set and erase them one by one. You don't need sets for this. It's okay to use sets here, but you don't need them actually. So you use sets in the same way you will use vectors actually. Yeah. So you just have a container. You need to put elements in the container. Yes. And you need to take all elements from the container one by one. Yes. Set can do this, yes, but again, set is overkill, so you don't need set. Set is very powerful structure, but it's for this problem it doesn't matter. For some another problem, you may have time limit because of using set instead of vectors. If you solve it next time, just try to minimize number of sets, just for educational reasons. In normal context, it's okay. In educational context, just try to solve using only vectors, just to learn how to do it. In some another problem, it may actually help you to get rid of some extra time limits because you have some extra log factor to your time complexity. So in problem F, we need to calculate some strange sum, something like this. And it would be okay to calculate sum just by using this formula. But you have n is very large, so n is up to 10 power 9. And they give you this sum by saying these elements Si are periodic. So we have some periodical sequence, k periodical. So we have given k elements of this sequence S, yeah? And we just need to repeat it until we have sequence of size n. K divides, yes, so it's divisible. It's actually doesn't matter that much. It just makes the problem easier, yes, but we can solve the same problem without this. That's it. So we need to calculate this sum, knowing that elements Si are some periodic. No. How you do it? Let's look at the sum. So what we have? So we have element Si multiplied by A in some power and by B in some power. Yeah? And these powers are monotonic. So B is in power I is just increasing by 1 every time. A is in power n minus 1, I. So A is decreasing. It's actually quite popular formula. You have something like this in some, I don't know, in some probability problems. Like you calculate like number of times something happens. Yeah. So you have some successes and failures. So this is probability of success, probability of failure. So you have I times you have positive result, n minus 1 times you have negative result. So you multiply probability of success power I, probability of failure power n minus 1. So this formula is actually quite useful. So what we do? Again, we can calculate this. So if this n is small, then we just can calculate this formula as is. So nothing actually is really scary in this formula. So we have n in some power. No, we can pre-calculate all powers of A. Why not? B in some power, the same. We can pre-calculate all powers of B. Yeah. So we multiply S by this, calculate this sum. We're done. Yeah. The only problem is this n is pretty large, so we can't calculate this sum explicitly. We need to do some tricks. What tricks do we do? Let's see. Let's start. So we have this formula. It's again, it's split it into okay. So we have some periods of size k. So we have k elements here, k elements here, k elements here. Right. We can calculate sum of the first period, for example. Yeah. So we have cell elements S0, S1, and so on, Sk minus 1. Yeah. So given these elements in the problem statement. Yeah, so we have this first k elements. Yeah, so we can just calculate the sum as is. So we can take all these numbers, multiply them by a, say in z power by b in z power, and calculate all of this. Nothing, no problems here. Now let's look at this sum. So we have the same elements here as 0, as 1, and so on, as k minus 1. But they are multiplied by different powers of a and b. Yeah? So in the first sum, we multiply s0 by n power n b power 0, plus s1 is multiplied by a power n minus 1 b power 1, plus and so on. Okay? In the second sum, coefficients will be shifted by k. So we will multiply s0 by n power n minus k, b power k. Yes, s1 will be multiplied by n power n minus k minus 1, b power k plus 1, and so on. Yeah. So we have kind of similar sum, but these coefficients from sequence S are multiplied by different powers of a and b. But if you look closer at these two sequences, the difference of these powers is actually the same. So if this sequence is A and this sequence is B, yeah, if you divide B by A, you will get the following. So in every element of this sum is different by, so B, so power of b is greater by k, so it was from 0 you get k, from 1 you get k plus 1, so you get b power k, and power of a is k smaller, so it was n minus k, so it multiplied by n powers minus k. So how we calculate the total sum? So we have the first sum, so let's say it's a. So let's name this somehow. Let's say this is x. Yeah. So this number is x. So here I have a. Here I have x multiplied by a. Here I will have x squared multiplied by a, and so on. Yeah. So you just need to calculate sum of let's say so. So let's a. So it's 1 plus x squared plus and so on. Yeah. So this is sum of geometrical progression. So how to calculate this sum? No, it depends. How you usually calculate sum of geometrical progression? No, usually calculate. So okay, if you never did this before, so you do it like this. So it's let's say sum is 1 plus x. Let's say x power 0 plus x power 1 plus and so on plus x power n minus 1. So imagine you have sum of n elements. So you have this geometrical progression. How you calculate this sum? No, you do it like this. So imagine this sum equals to some value. Which letter I don't have? I have the letter m. Why not? So if I take this sum and multiply it by x, so I will get x 1 plus x power 2 plus and so on plus x power n. Yeah? So it will be m multiplied by x. So now this sum is almost the same as this sum. So if I subtract mx minus m, so from this sum I subtract this sum, I get this xn, everything here will be eliminated by this, and I get minus x. So it's just x power n minus 1. And from here you get m. So m is just xn minus 1 divided by x minus 1. Again, this is, so you probably saw this formula before, it's sum of geometrical progression. So I just show you how you get formula for geometrical progression. You probably know this formula, so it's not a big problem. So again, the whole solution works like this. I split my sum into segments, calculate sum of the first segment. Now, sum for every next segment is the previous sum multiplied by some number x. So here is number x. So the sum I need to calculate is the sum of the first segment multiplied by some geometrical progression. You can calculate some geometrical progression like here. Good. It's actually almost correct. You sum of geometrical progression is always like this, except when x equals to 1. When x equals to 1, you cannot do it like this, because you have 0 divided by 0. But if x equals to 1, this sum is just equals to n. This important special case actually when you calculate sum of geometrical progressions. No, that's it. So now basically we have all the formulas. Let's just implement it. So we have integers n, a, b, k. Now I need to do a lot of modulo calculations. So all the calculations are made modulo 10 power 9 plus 9. So normally I would just copy my code from, I have some pre-written code for modulo calculations, but I will just do it from scratch for you. So I will do everything modulo m. So I have const, let's say, do it in longs. Mod equal 10 power 9 plus 9. Let's do it like this. Why not? It's double. Here I can cause double to longs. Not the best way to program, but it's fine. Now let's make struct. So I don't forget to calculate something modulo. I will just make a special struct which will calculate everything modulo. So the mint and it had long x, and I will have mint of long. Not the best way to program, I know. It's not the best code in the world, but it will work. If x less than 0, x plus no. I do this because here I can drop some negative values and it still will be fine. Okay. And now what we need? We need some operators. Let's add some operators here. Let's say mint operator plus for mint a, let's say return x plus ax, like this. Simple. So when if you write code for your pre-written library, you better do something more optimal. I just do it from scratch, so I do it not the best way to program again, but it will work for this problem. Okay, not the best code, but it's okay code. Now we need to divide. Sometimes we need to divide. Yeah. So I will add the operator power. So I'll mint power, let's say and let's see, A and B. I don't know. I'm boring today. Let's see, long. So I add. So you can call power. No. What's the problem? Okay. Okay. Normal binary exponentiation. So you have binary res equal 1. Now while b is greater than 0, you check if b and 1. You say res equal res multiplied by a equal a multiplied by a, b divided by 2. Res. Just normal code to calculate power of number. And finally, I need to divide, so I can mint inverse. I will say just, no, you can do it like this. So when you have prime model, you can just mutate mod -2. Good enough. I believe that's all modular arithmetics I need in this problem. Now let's move to the problem actually. So what we have, they have n. Let's move AB to some means, especially AB. And okay, yes, thing S. Now let's calculate sum of the first segment. I already have S. Oh. So how called A? Okay, so let's do it like we did here. So sum of the same will be A equals 0. Can I do it just like this? I think I can. Let's do it just like we discussed. So we'll multiply. Okay, so A plus. So I need value as 0. Okay, means Si will be Si equals this. So I need to direct this Si multiplied by power of A in power n minus I multiplied by power of B I. Just like this. I think it will work even like this. So it's not the best. You can pre-calculate all the powers, but you don't call this power every time. So here I have additional logarithm operations in this power. You can improve this. You can just get this out. So every time you move from one power to another, so you can easily recalculate it, but I will not do it. Now I need this. I need this number x. So this number x will be like here. It will be power of b k multiplied by power by inverse of power of a k. Now I need to calculate these. So I need two options. So if x equals to 1, then I have special case. I have this geometrical progression with coefficient 1. Means as sum. Okay. Then sum you can do it like this. Okay. Will be equal to n plus 1 over k. Yeah? Just number of elements. Yeah. And if not, then sum will be equal to this. Yeah? Here, you take x power n. N is number of elements, so it's n plus 1 over k minus 1 multiplied by inverse of x minus 1. I just write it like I do here, yeah. So you just basically move from this formula to main code. It's actually very natural. And just my result is just a multiplied by sum. And I need to output should work. Yeah, looks okay. So again, it looks like a scary problem with some modular arithmetics and stuff, but it's actually not. So modular arithmetics is actually not that hard. So you can do this once and just reuse the same code every contest. I just wrote it from scratch for you in a few minutes. It's not that complicated. Yeah. So you make simple math operations. You see binary exponentiation. You calculate inverse values. That's it. So that's all you need for 99% of the problems. And here, nothing really interesting. Here I simply calculate the sum, like I normally do. Here I calculate sum of geometrical progression. Again, it's easy formula. I'll check what's happening. Sorry, 1 minute. Show my dog. Say hello. She wants to go for the walk. But it's not yet. We need to solve 2 problems. Are you ready? Let's go. Go? Okay, we need to solve 2 more problems. If we do it fast, we can go for the walk. Okay, so problem G. So what we have in problem G? We have some, we have some long problem statement about some dogs. So the dogs, so they move from left to right. Every time you go to some position, they have some ball. And for each ball, we have this value ti. So its amount of seconds, we need to wait till this ball is eatable. So, yeah, so we can wait. If the ball is not eatable yet, we can wait until it becomes eatable, and then we continue. The question is, after 3 seconds, cannot eat. So we can eat all the balls up to moment t. So for moment t is we need to stop, and we need to find the maximal number of balls we can actually eat. Yes, yes. So we need to find the maximal number of balls we can eat from in the first t seconds. Nice. So we start in position 0. Nice, and balls located in positions from 1 to n. Okay, everything looks natural. So we start in position 0 and we have some balls, and we move from left to right. We're not allowed to move to the left, and we eat some food. So every time we can eat the food, or wait till if it's not yet ready, we can wait. Well, let's think. First, let's think about some simple solutions. So imagine you go from left to right. So if you want to find any solution, not just optimal solution. So it looks like we need some optimal solutions because n is up to 200,000. So we need to do something fast. Yes. But if we don't think about time complexity, and before you learn how to solve problem with intended time complexity, let's try to solve it with any time complexity. Let's make some slow solution. Yeah? So how do you make slow solution? Well, let's do it like this. Let's go from left to right. Yeah? So we go from left to right. Boom, 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 boom. Let's say this is position 0, this is position. So here I have the balls. So we go from left to right and eat some of the food from these balls. If we go to position, so what is our current state? Yes, our current state is the position we're in and the current time. Yeah? So we can make kind of dynamic programming. So we have dynamic programming from the current position and current time. So if we stand here at this moment of time, yeah, we can check if it's possible to eat this food or go, or we can wait. Yeah? So we can stand here or we can wait. Looks fine. It will give us at least some n square solution. So if we do it like this, so we have n square number of states. Okay, hope it's clear enough. Yes, is it clear enough? Now we just need to improve this time complexity. So you have some dynamic programming problem, and you need to improve time complexity from n square to something suitable like to linear complexity or n log n time complexity. Here n log n will work just fine, so n log n also fine. There are multiple ways to improve time complexity from n squared to n log n. So again, first when you read the problem statement like this, you think about any solution, probably not the optimal one. Okay, so you find the solution works in n squared. That's good. So you have some solution. Yeah, it's not yet correct solution. It's not optimal enough, but it solves your problem. Yeah. So what you need to do next is just to improve your solution. To improve the solution, let's see how we calculate these values. So let's see how we calculate these values. Just think, what is the easiest way to solve this problem? Okay, I didn't solve this problem before, so I will solve it with you. So I'll just show you how I think when I solve problems like this. So what I would do, I will just write how I calculate these values. So di time is calculated. So I'm standing here at time and time, yeah? So how I calculate these values? Okay, let's do it in a hard way. So di time. So I'm standing here at time I. I will do it like this. I will go from ball to ball, from left to right. Yeah. So I go from left to right. Every time I step out, I look what was the previous time. So I wanna do it like this. So okay, let's do it like this. Let's do it like this. So imagine we have 4 neighbors. So we're standing here at time. Now imagine I come to this place at this time. Yeah. So what I'm doing, if time is greater or equal than ti, then this ball is already ready. Yeah. So I can eat it and go to the next ball. Yeah. So I just move to di plus 1 time plus 1. If time is less than ti, then I have 2 options. I can go to the next, again, I go to the next ball, plus just number of balls, plus 1. So I eat this ball and go to the next, yeah? So, or I cannot eat this ball, just go to the next ball immediately. Or I can wait. If I wait, I go to the next ball at time ti plus 1 and plus 1 here. Good problem. No, okay. Let's move from here. I'm trying to find the easiest solution, but I didn't. So okay. Let's finish this one. So what I'm doing here. So now I look at this picture. So I go from di to di plus 1. Yeah. So I look how this transformation it looks when I make all these transitions. Yeah. So here you have state I, yeah. So this is di. It's just set of states. So here is time. Yeah. So you move from this state to state di plus 1. Basically, you make the next row of your dynamic programming. So how you do the next row of dynamic programming? So here you have the position ti. Yeah. So starting from this position, you just make plus 1 to everything here. Yeah. So for all these positions, you make this position plus 1. If time is less than di, then you can just +1. Let's mark them as red. So this red is +1. Okay, it's hard to understand, but okay, I'll draw the next picture. Will be better. Now, for all positions to the left from STI, I just copy them here. Yeah, here. And I kind of want from every position here, I want to go here, eat this ball, and go to this position. So they all also have transition to here +1. I just found easy solution. Okay. I'll finish this first. I will finish this solution first, and then we'll talk about easy solution. Okay, I'm stupid today, but okay, we'll finish this solution first, and then we'll talk about easy solution. So now let's see what's happening here. So again, you have this current layer. Let me write it once again. So you have this layer di. Yeah. So what you do when you calculate the layer di +1? So you take this suffix, yes, and move it one position to the right and add +1 to it. So you move this suffix here and make +1. Yeah. Suffix start from position ti. And also you take this prefix here and just move it here, again shifting one position to the right. Also, you need to be able to wait here to this point and then just go here. But it's easy to see that actually this array is not decreasing. If you spend more time, you just eat more. So this array is not decreasing, so it's never optimal to do this. So you never stand here and go to this position and then move here. So actually what's happening is just you take some suffix of your array, increase it by 1, and then move to the next state by shifting everything one position to the right. Okay, it's too complicated. Okay, I get it. Okay, now easy solution. No, actually, you can do all this by basic data structures. Actually, so you can maintain the current layer. You need to shift it one position to the right, and then increase suffix by 1. Okay, easy observation is actually, yes, I found only now that this array is non-decreasing. It means it's never optimal to wait in some wall. So if you come to some ball and then wait until this ball is actually ready to eat, you can just wait in the beginning. Yeah. So if you look at your progress, so you start here, you go here, then wait, go here and wait, go here and wait. So at some point you wait till the ball is ready to eat. Instead of doing this, you can just wait in the beginning and immediately go here. Yeah? If you do it like this, then all these balls will be already ready to eat. So you don't need to wait in the middle. You wait only in the beginning. Okay, this observation actually makes everything much easier. Okay, so if you wait only in the beginning, then you just need to choose how much time you wait in the beginning. Yeah. So you wait some time in the beginning, then you go and eat everything you see. Yeah. And you just need to choose how much time you wait to get as much food as possible. Let's see. How much time do we wait to begin? No, we made let's call it somehow. Let's call it x again. So imagine optimal solution always works like this. Optimal solution always looks like this. We start in the beginning, wait X seconds, just till everything is cooled down, yeah, and then walk and eat everything we see. Yeah. So if we wait X seconds, then we need to have moment T. So if we wait X seconds, then we can walk to the first T minus X balls, right? So we wait moment T. Yeah. So we eat everything in the first T minus X balls if it is already cooled down. Makes sense, yes. Now, how to choose this value X? No, we choose this value X, so we come to some ball. Is it actually? No, okay. Now there are multiple ways to do it. So since we have the positions x11 in 1 second, you can actually see that it's never optimal to wait a small amount of time. So this t minus x should be not greater than n. Yes. Because if you have t minus x equal to n, you can just eat everything. Yeah. It just okay. T minus so you don't eat so. I forgot. Show stop some best user. T sense dog reaches the ball moment t cannot eat. So we see from 0 to t minus 1. So again, so with t second n minus 1. Yes. No, plus 1. Again, final moment is t minus 1. So t minus x minus 1. So if we spend x seconds in the beginning, so this is the final moment. And we should reach the last element here. Yeah. So it must be less or equal than n. If it's greater than n, I can wait 1 second more and still reach all the balls. Okay. So it means x should be greater or equal than t minus n minus 1. Yeah. And also x is not greater than t, obviously, yes. So there are just n possible values of x. So we can just check all possible interesting values of x. And if I know value of x, I know which balls I can eat. And I just need to find number of balls I can eat on this prefix. Okay, this problem is actually much harder than I expected. How many people solved this actually? Only one, okay. Well, I will not read your solution. Let me write my solution first. Okay, problem G is hard. I agree. Do we have time to write this solution actually? We're already 2 hours in this lecture. No, okay, let's do it. And we have t. Okay, let's make it capital T like here, and now we have small t. Okay, now, okay, let's just pick all possible values of x. So x should be in this region. Okay, let's for int x from t minus n minus 1 t x plus plus. X is less than t. Okay. If it's equal to t, I can do anything. It's boring. So I wait that many seconds in the beginning and then go here. Yeah. Now, for each ball, let's find the minimal value of x. I need to make it work. So a minus n. So minimal value of x for this ball is equal to, so I need this ball to be ready if I wait x, again, if I wait x minutes here, then I go to this ball I reach this ball I by time x plus I plus 1, yes, because I plus 1, and this time should be greater or equal than ti, yeah? It means x should be greater or equal than ti minus I minus 1. Yeah? So this is the minimal time when this ball is ready to eat. Yeah? Now I check if this min x is less or equal, let's say, than this value, minimal value for x. I will just count it as in the beginning. Oh, I don't like this. Okay. I can do it like this. Okay. So I need to put all these pairs in array. I don't like this problem anymore. No, okay. So I'll just put all these pairs in this array P. You'll see. So I put this pair of min x and I. Okay. Now, what I need to do? I need to recalculate number of accessible balls every time I increase this value key x. Yeah. So for every value x, I need to maintain set of good balls. Yes, balls I can actually access right now. So if I'm standing in ball x, the maximal distance I can track. So let's say d. So the last ball I can go to is actually t minus x minus 1. Yeah. So I can access all balls from 0 to d. So I need to maintain number of good balls in this prefix. So to do this, I will add these balls. So some balls become accessible when x is increasing. Then I increase x, some balls become accessible. So I will maintain balls of which are currently accessible. So I will just sort this array P, and it will go from left to right when I increase value of x, and add more good balls to my set. Ooh, much harder problem than expected. Okay, let's go. So first, I will do it like this. So I'll say while j is less than n, and pj is my current new ball. So if so this is the first time this ball became accessible. So if this first time is less or equal than x, it means now this ball is accessible. I will mark it as accessible. Yeah. So let's say g. Let's make it g of pg second. So again, for every ball, I calculated the first time this ball became accessible, sort this by this time, then every time I increase number x, I make new accessible balls, just mark them as accessible over here. Oh, let's move this here. Now I need to find number of accessible balls in my prefix. Yeah. Nice problem. Nice problem. So now every time I create new accessible ball, I check if its index is not greater than d, then I get new accessible ball. Now, when I finish, I decrease this d by 1. Yeah, so I go to next x, decrease this d by 1. So I need to update value of, so if the last ball, if was good, I need to decrease. Okay. So here I find new accessible balls and mark them as good. And if this ball belongs to my region, I increase this counter. Now I shorten my segment by 1. So I remove one element from my segment. If it was good, I need again to update my counter. Okay. And here I will update result. Something like this. Let's hope it works. X is -1. X can be -1. Maximum of this and 0. Yes, I cannot wait -1 seconds. Okay. That makes sense. It shouldn't be. Oh, still, what? -2. Okay. Here also. Boom. Why? So I could put this one. So I put. So when I go here, I hate this problem even more. I'm not that sure about this problem, but no. Oh, it's embarrassing. It's so embarrassing. Okay. Let's finish this first, right? And then you increase d. Okay, that problem turned out to be much harder than expected. Let's check your solutions actually. Oh, it looks much easier. R and T at solve dt. Okay, this is something similar. So you put these times here. So just maintain this set. This set. Okay. Yeah. Okay. This okay. It's actually you're doing the same, but maybe a little bit easier. Maintain this multi-set. I just do it by sorting all values and going like this. Okay. Final one. So in the final problem, we need to calculate something something strange. So we calculate. We have some numbers. We take all possible subsets. All possible subsets. We have k and we create common divisor greater than 1 for some reason. And then we calculate the strength like this. So we take this greatest common divisor, multiply it by number of elements in this set. So k is the same number of elements. And this is like the strength of this subset. And when we just need to calculate strength of all possible. So now we need to calculate sum of all possible strength of all the subsets. So we take all subsets, calculate this value, and calculate sum of all these values for all subsets. let's look here. For example, in the first case, I can take number 3 and number 3. It's boring. Yeah. So they all have greatest common divisor equal to 3. And I have 3 sets with great common divisor equal to 2, and it equals to 1 and 1 and 2. So here's number of elements in this set. So okay. So when you see a problem like this, you think about some similar problems. So similar problems I know looks like this. So again, what you do in these problems, you need to look at all subsets and consider the greatest common divisor of these elements, and calculate some sum. Again, it's about sum calculation. You have some strange sum, and you need to calculate it. Yes, and you do it by combining similar elements of this sum, and we will combine elements with the same greatest common divisor. So this greatest common divisor is not greater than all my elements, and my elements up to 1 million. So there are just million possible values of this great common divisor. So I will just check all of them. So for every value of this great common divisor, I will find the sum of all possible sizes of the sets with the same greatest common divisor. And you do it like this. Do it like this. So consider some set of elements. So again, you have all your elements, yeah. So you pick some subset, yeah, and consider this subset. This subset has some greatest common divisor, yeah, and I want to calculate for this greatest common divisor the number of elements in this set and add it here, yeah. Now the trick is like this. So instead of considering all possible greatest common divisors, I will consider all possible divisors, not greatest, just common divisors. So imagine D is just common divisor. How to check if D is not greatest common divisor? No, D if not greatest, if there is another divisor which is greater. Yeah. So I will do it like this. I will take some subset. Yeah, imagine you have some subset, and all elements are divisible by D. So I take all elements are divisible by D. Yeah. So if all elements are divisible by D, then they have common divisor D. Yeah. Now, how to check if they don't have any other common divisor? No, I will check all multiples by D, 2, 3D, 4D, and so on. And just subtract all these elements. So if some set have common divisor 4D, it also have common divisor D. Yeah. So I will check all sets that have these common divisors and subtract them from here. If I subtract everything except D, I will leave only D. So I will take all the numbers with common divisor D and then subtract all elements with common divisor greater than D. If you do it like this, you will leave only elements with greatest common divisor equal to D, because they have common divisor D and they don't have any greater common divisor. Let me show that. No, first of all, we need to calculate for them. We need to calculate for every divisor, calculate total size of all sets that have this common divisor. No, we do it like this. Let's calculate number of elements that are divisible by D. Let's do it one by one actually. So n and n elements. Okay. Let's calculate elements. Now, for every value D, I need to calculate, so every D. From 1? We don't need 1. From 2. We don't need common divisor 2 because of the problem statement. Max D plus plus. Let's see, const. Equal million. Yeah. let's say $1,000,001, and I will hold less than max, like this. So I always have right border non-inclusive. Yeah. Now for every value d, I want to find number of elements divisible by d. And I will do it like this. I will do element dd equal d, dd less than max, dd plus equal d. So I'll check all multiples of d and just add infinity of max, infinity of d plus equals infinity of, let's put them in the same counter for simplicity. I need to count elements first, like this. Yeah. So first I count elements, and here I count these sums. So for every element, so for every value d, I count number of elements divisible by d. Yeah. Do you believe? Now, I know number of elements. Now, what I need? I need to calculate total size of all sets, that's interesting, that have this common divisor. Well, let's do. So, what's easiest ways to do it? I don't know actually. Total size of all sets. I don't know easy way to calculate it. If you know, sure, tell me in comments, okay? Is there easy way to calculate it? So what I want to do, I want to, I need to find size of this set and multiply it by number of choices of this set. Let's do it like this, okay. So k is number of elements, so it's int of d. I want to choose, okay, not k, let's say p number of elements, yeah. I want to choose k from 0 up to p elements. And calculate number of ways to choose k from p. So it's, I need binomial coefficient. Let's steal it from another problem. We already did modular arithmetics today. I don't want to do it again. Oh, come on. Where was it? Here. Let's just copy from here. Model we have +7. Okay, so what I need to calculate binomial coefficients here. So I will calculate factorials. Factorials up to n plus 1. Just normal calculation of factorials. And then calculate invert factorials, because it's just faster. So I don't need to invert it every time. inverse. Now here I need to calculate binomial coefficient, so mean, let's say R, of number of ways to choose k elements from P. Yeah? It's factorial of P divided by inverted factorial of k and by inverted factorial of P minus k. Okay? So it's number of ways to choose k elements out of P. And now I just to multiply this R by k. Yeah. So okay, so it is total size of all sets, and just let's put it somewhere. So D, I already have D. Okay, let's say this side like this. So it's equal plus equal. Like this. Yeah. So again, for every divisor, I calculated the so this is number of elements divisible by this D, and here I calculated total number of total size of all subsets divisible by this D. Yeah. Now again, this is not the correct answer. Okay, let's actually check them. Let's solve this. Hop. But it's boring. Okay, let's check it. Let's make max smaller. Let's make it 10 for now, so we can check. What? That's fine. Where? What? I don't have empty constructor. Okay. It's like this. What now? Okay. Now, for divisor 3, I have sets of total size 4. It makes sense. Yes, I have sets of size 1, 1, and 2 in total 4. And for the second one, so I have sets divisible by 2. Yeah, I have 2, 4, and 6. Yeah, so I have 3 elements divisible by 2. I have 1, 1, 1, it's 3. I have 2, 2, 2, it's plus 6. Oh, no, that's not. Yes, 3 plus 6 is 9, and plus 3 it's 12. I just found out it's actually quite easy to calculate this sum. Okay, I overcomplicate this thing, so let's simplify this. So how to calculate total size of all sets? Let's calculate the number of sets each element belongs to. Each element belongs to all sets, including this element and something else. Yeah. So okay. So ds of D is just equals to size of number of elements multiplied by 2 power 2 p minus 1. Yes, if p is greater than 0. Yeah, I think it should work. It's actually easier. What? I forgot to print. Yeah, look at the same. Okay, so it's easier problem. Finally, now we just remove all, or we just go. I will go from right to left. And remove everything. I will do this step. So I will take number d and remove everything which is greater than d. So dd equal to 2d, dd less than max. So I'll take all the multiples of d and just remove them from my set. So I'll ds d minus equal ds. Okay, I didn't make minus equal. D minus ds d. So in the end, I have good results. So I removed all elements, or all sets which have bigger common divisor from my set. So my result, let's calculate result finally. Plus dsd multiplied by d. I think I overcomplicate this problem actually. Yeah, probably. Runtime error, it's interesting. Be careful when you do it like this. So I change maximum to small value for debug purposes and then forgot to put it back. Okay, and now I submitted solution with this part. Okay. And this also. Yeah, I think they both work. Okay, so this part with this complicated calculation, and this was okay. It's a little bit faster, but not that dramatically. Okay, not that many people survived this discussion. So thank you for joining me today. It was a much harder contest than I expected, but it was fun. It was fun. So I believe we learned a lot of new tricks today. Okay, so see you next week.